Alright, SBI4U. This is the first video of our new unit, which is called homeostasis. Here's how you spell that, homeostasis. This unit is all about how our bodies sense the external environment and then react to it, and the goal is to keep our bodies at a certain set point. It's a really interesting unit. I really like it. So let's just jump in. We're going to look at our learning goals here. First off, we're going to do an overview of homeostasis concepts, what it is, why it's important. Then we're going to do some examples of different homeostatic mechanisms in humans, all the ones that the curriculum wants you to know. We'll talk about feedback systems and the components of a feedback system. Then we'll get into the difference between negative and positive feedback. That's an important difference. And finally, we're going to take a deeper look at one of the homeostatic mechanisms, which is thermoregulation, which is how we regulate our body temperature, keep our body temperature at 37 degrees Celsius. It's going to be a short video because it's coming hot off the heels of a test and I didn't want you guys to have too much to think about. So let me take that away and let's go. So first off, why do we want to keep homeostasis? Well, if we have the same environment inside ourselves within certain parameters, then we are more efficient. We can have enzymes that work at specific temperatures, enzymes that work at specific pHs. So that's one of the things. And if it goes too far out of line, the cells, the enzymes, and the molecular stuff that we do might not work properly and it'll result in death. So as an example, if it's very hot in the body, the cell membrane might become too fluid, and then the cells will be too flexible, and maybe they won't be as tough anymore, and they'll start falling apart. Or the other way, if it gets too cold, they'll get too stiff, and they won't be able to move as easily. This is why your hands get stiff in the cold. It's also why cooking meat makes it easier to eat, because the heat will break up those connections between cells by making membranes more fluid and stuff. So we regulate it and we maintain optimum conditions for all of the biochemical reactions. So a lot of our enzymes work very well at 37 degrees Celsius because that's body temperature. And the homeostasis, the definition of it, is this tendency to maintain internal stability within narrow limits through a coordinated response of its parts. It was termed by this guy, Walter Cannon, homeo for Greek from the same, and stasis for standing still, so it's staying at one place. It's almost like standing still and standing still. It's like two words that mean the same thing. Here's a flowchart of what normally happens. You can start at any point in this flowchart, but typically here is where most people start it, is conditions in the body change from a set point. So I'm sitting here at 37 degrees Celsius. Let's say I open a window. There you go. I opened my window. Now the outside air is going to flow in. My room's going to get colder. What's going to happen? Well, eventually my body is going to get colder because now it's colder air in the room. Something's going to have to detect that change. I can already feel it getting colder. And then some kind of corrective mechanism gets activated. That corrective mechanism does its work, bring the conditions back, and then the corrective mechanism switches off. So if it gets really cold in here, I might start to shiver. Right? That's the corrective mechanism. The shivering will heat up my body. Once my body's warm enough, I'll stop shivering. But if the window's still open, right, the body conditions will change again, and then I'll shiver again, and they'll turn off again. So I'll just spend time shivering and then stopping to shiver, shivering and stopping to shiver. That's homeostasis in a nutshell. Here's, the other way. So there's shivering for cold. There's sweating for hot. If it gets really hot in here, I will sweat until I'm cold enough. Then I'll stop sweating, but then I'll get hot again. Then I'll sweat, and it kind of goes in a figure eight around the optimal temperature. So, we try to keep 37, but we're always going to be a little bit higher or lower, and we're just kind of keeping it within a range. Right? So what kind of systems are needed to make this happen? Let's use that shivering example. Right? It's getting colder in here. I'm going to start shivering. I'm going to start trying to make more energy. First things first, something has to sense that the outside environment has changed, that the inside of the body is now changing because of the outside environment. For the thermal response, that is my skin receptors, right? I've got temperature receptors in my skin and also inside me that tell me that heat is flowing out of my body. Too much heat is flowing out of my body. Then something has to relay that signal from the receptor to my brain, right? So there needs to be not just a receptor here, but that receptor needs to travel all the way up my arm and into my brain somewhere. It's actually down here, it's in the brainstem. And that's the other part, the second part. Something has to make it travel. Then the brain has to make a decision for what to activate. So there needs to be a whole bunch of little processing that happens in here, like a little computer. And then a different pathway needs to send that signal that the brain decides on back out, and then start my hands shaking or start me shivering or whatever is going to happen there. So it's it's an important thing. And then after that happens, another thing has to detect that now we don't need the mechanism anymore. Something has to detect that the body is back to normal. And then it has to send a signal back to the brain to shut off the shivering that the brain started in the first place. And then the brain has to send the signal to shut off the shivering back to the muscle that started shivering. So it seems on the surface, when you see a diagram like this, fairly simple, but there is a very complicated physiological response here. So here's some examples of different homeostatic mechanisms that we are going to talk about. The one that we're going to cover today is body temperature, but we're also going to talk about blood glucose, done by the pancreas, pH, which is done by the kidneys, water balance, which is also done by the kidneys, and ion concentration, which is also done by the kidneys. So a lot of this is kidneys. Kidneys are our big organ. This unit we're going to talk about the function of the kidney, the structure of the kidney, what it looks like in there. How do the kidneys actually filter our blood? One last piece here is that the set point that we have in homeostasis is not necessarily unchangeable. Right? 37 degrees is the typical human body temperature. It's actually like 36.5 now, something like that. And we're usually going up and down around that 37, but if the body decides that it wants a higher set point, it can do that. The control system up here in our brain can decide, oh, I want the set point to be like 39 degrees for a little while. And it does this when it wants to make a fever. So it's an important thing in the immune response. When you make a fever, your body cells can still function at like 39 degrees, but the bacteria that are attacking you might not work so well. So it's a helpful thing. And if the infection continues, the body just keeps ramping that fever up and up and up to try to kill those things, and eventually the fever can actually get dangerous for us. Here's a flow chart of this. Remember, I talked about how you need something to detect it, something to send a signal, something to affect the change, and then something to check the signal, make sure to turn it off. So here's where it starts, right? Something gets into the blood that the body recognizes as an immune response. The white blood cells will eat it. The white blood cells, when they eat it, they're the receptor. They send out this thing called a pyrogen. The pyrogen in that area releases prostaglandins. The prostaglandins travel through the blood up to the brain, to the hypothalamus, and the hypothalamus starts ramping up the set point of your body temperature. It sends out signals to the muscles to start shivering. It sends out signals to your blood vessels to constrict. All of the outside blood vessels, like in your hands and your nose and your lips and stuff, they constrict to make more of your blood flow into your core. And it also kicks up metabolism, so your cells in general just start using more sugar. And that makes the temperature go up because we're wasting heat. The second law of thermodynamics says that every process produces heat. The temperature will go up. And at the same time, you're actually making more white blood cells in the immune system. And if there's more white blood cells eating more things, they're releasing more pyrogen. And so you'll end up ramping the fever up and up and up. And hopefully you take out whatever is infecting you before the fever messes you up. Yeah, if it's a particularly bad fever response, we have to actually put in drugs to reduce the fever response, which is basically the counteracting chemicals to this, because the hypothalamus can release the opposite. It can release chemicals that reduce a fever. Yeah. So we're going to get into feedback systems. So that's our next topic. I'm going to pause. Okay, we're into our next topic, which is feedback systems in homeostasis. And every feedback system can be broken down into three things: a receptor, a control center, and an effector. And you can have multiple receptors, you can have multiple effectors. So for example, in the thermoregulation, you can have skin receptors for temperature and internal receptors for temperature. You can have multiple effectors as well. So you can have the shivering response. You can also have the vasoconstriction response to keep the blood in the core and get it warmer. But typically there's only one control center, typically just one thing, usually in the brain, monitors these things and sends out the appropriate signals to change them. So here's the components. For example, receptors are often nerves in the skin or the eyes or wherever they might be. It'll detect different changes. The control center is usually in the brain, but not always. So for example, the glucose is controlled purely in the pancreas. Your brain doesn't get involved in regulating blood glucose. And that decides a response. And then the effector is all kinds of different things. It can be muscles, organs, glands. Sometimes a feedback system will feed back to the receptor, and it performs the response. And then the control center can check again and see if it needs to continue that. Here's the general mechanism. First you have to detect the stress by the receptor. Then the receptor sends the message to the control center, usually with a nerve, sometimes with a hormone. The control center then decides what to do through a complicated series of steps. It's going to be connected somehow to the effector, so the control center has to be connected to both the receptor and the effector. The effector will respond to it, and sometimes the effector will send feedback back to the receptor to be like, hey, you should check again and send a new signal to the control center. Yeah. So that's important. The receptor has to kind of check over and over again to make sure that whatever desired effect has been done, because the control center won't know unless the receptor tells it that things are okay. Yeah, let's talk about positive versus negative feedback. I'm gonna pause again. Okay, we're back. We're talking about positive versus negative feedback. Just a little keep in mind up here, negative feedback is what we normally use to keep a set point, and positive feedback will produce some kind of acceleration. So typically we want negative feedback. Positive feedback is rarely a good thing. So an example of a positive feedback loop was that fever response with the white blood cells. When you have an immune system thing, part of the response is making more white blood cells. The white blood cells make more of an immune response, and you get this positive feedback to accelerate how many white blood cells you've got coming out. But yeah, most of the time negative feedback. We want to stay around a set point. Here's how a negative feedback loop works. It typically looks like a figure 8 because we want to be able to pull it back up if it's low and push it back down when it's high. So the negative feedback loop is done through the liver and the pancreas. Notice that there's no brain involvement here at all. It's just done automatically by your pancreas and your liver. The pancreas detects the change in blood sugar and releases insulin if there's too much blood sugar, and then the liver will store the glucose as glycogen. So will the cells. And then if it falls back down, then the pancreas stops releasing insulin and it's fine. If there's too little blood sugar, the pancreas will release a different thing called glucagon. The glucagon will stimulate the opposite effect in the liver, but only in the liver, not in the tissues. And then it'll come back out. So this is our receptor and our control center in the same time. This is the signal. That's the effector. So it's kind of a cool little thing. It's a neat negative feedback loop. Positive feedback, though, is for acceleration. So for example, the cheetah is chasing the little antelope here. The cheetah runs faster, so the antelope starts running faster, so the cheetah starts running faster, so the antelope starts running faster, so the cheetah, you get the idea. You get the idea. They feed off of each other in terms of getting faster and faster and faster. Another example is if you're in a loud room and someone starts talking louder to be heard, and then everyone starts talking louder to be heard, and then the entire room basically starts yelling. That's another positive feedback loop. Positive feedback, usually not great. To kind of show this off, here's a positive feedback loop in anxiety or in PTSD. Basically what happens is something happens and your brain decides to trigger the anxiety response. That releases like adrenaline and things like that into your brain. That adrenaline makes your heart rate go up, makes your breathing go faster, you start kind of, getting jittery and stuff. And then your brain feels that and goes, I'm really feeling jittery and stuff. There must be something out there to be afraid of. And then it looks out, it uses its senses to look out into the world. And now it's kind of keyed in to be like, hey, there should be something dangerous out here. And then if it doesn't see anything dangerous, instead of doing the natural thing where it says, oh, okay, I guess it wasn't a big deal. In some people, people that have anxiety disorders or are having a panic attack right now or whatever, the brain goes, it must be hidden. It must be something hidden. And then increase the anxiety even more. And then you just get this feedback loop of adrenaline and anxiety. Same thing happens in PTSD, where the original perception of the environment as dangerous just gets multiplied by the fact that the brain thinks that it should be worrying. Very difficult cycle to break because you can't just tell your brain to stop. It's a very kind of primal thing. That's an example of a feedback loop that's doing a bad thing. There are examples of feedback loops that do good things. So for example, here is a baby in the womb, and the baby's big enough to get born. When the baby's head bumps up against the cervix has nerves in it, and it sends the nerve signal up to the brain. The brain produces oxytocin. The oxytocin comes down to the uterus, and the uterus then contracts harder. The muscles in the uterus will now start pushing harder. That pushes the head against the cervix harder, which sends more of these signals to the brain, which means more oxytocin, which means more contractions, which means more oxytocin, and then that increases the strength of the contractions until the baby is out. Once the baby is out, then there's nothing pushing against this, and everything goes back to normal, basically. So sometimes positive feedback loop is used for good in the body and the brain, but most of the time it leads to kind of runaway issues. Now we're going to get to the last thing, which is thermoregulation. So I'm going to stop for a second. Okay, so very quickly we're going to go through thermoregulation. Thermoregulation is keeping body temperature within a range, a pretty narrow range, but wider than you think. This is negative feedback because it's trying to hold a set point. We are warm-blooded, we're endotherms, we keep a constant body temperature. There are cold-blooded animals out there, like fish and reptiles, that can't maintain a constant temperature. Their thermoregulation is mostly by like going out and finding shade or sun to go to. They hide during the day and they come out at night and things like that. But for us, we can do other things to maintain our body temperature at that set point. When it gets really bad, we can't protect ourselves. Like no matter how much thermoregulation our body wants to do, going outside when it's like -40, you're going to get hypothermia. Going outside and being outside in like a sweater when it's +40, you might get hyperthermia. It's the opposite. We do have this interesting reflex called the mammalian diving reflex that slows down our heart and conserves blood in our core when it's really, really cold. And so certain small children have survived in icy water for very, very long amounts of time because of this. But when you're a big adult and you've got a lot of cell processes going on, you're going to die pretty quick. Other adaptations include hibernation and torpor and estivation. Torpor is temporary. Hibernation is much longer. But otherwise they're very, very similar. And estivation is just a summer version of hibernation. Estivation is like été, like in French. Hiver, like in French. So some things actually end up doing like the opposite of hibernation. Here's a thermoregulation system. It's mostly based on sweat glands, muscles, and the arterioles that can contract in the extremities. When it's too hot, the arterioles dilate, and so a lot of blood goes to our extremities. That's why things get red. You're seeing a lot of blood in the face and on the arm, on the hands and stuff. You're sweating because the water is evaporating off you, and that cools down the body. When it's too cold, your muscles start shivering. And because we're just wasting energy shivering our muscles, that waste energy turns into heat, right? The second law of thermodynamics, so that heats us up. And also the skin in that case will, the blood vessels on the outside will constrict so that the blood stays near the core where all of the important stuff happens. It's okay to lose a few fingers if you can keep the body alive, is basically the idea there. And this is all done in the brain. In the thalamus in the brain, the hypothalamus in the brain. So you can identify the three main parts, right? The receptor, the control center, and the effector, and the general flow. And then there's going to be feedback as well, right? The feedback has to come back to the thermoreceptors to detect this temperature. One of the weird things we have is the erector pili muscles in our skin. You get goosebumps when you're cold. That's an evolutionary holdover for when we had more fur, and sticking the fur up was actually a way to get more insulation. So you'll get goosebumps when you're cold because of it. There's a video from the Amoeba Sisters about this, which is really, really good, so I'll link that down below. This was a really short video, once again, just because it was a review, or just an introduction, and also because you guys are probably finishing up the test instead of watching this video. So, I'll see you guys in class, and thanks for listening.